Hello and welcome to the second lecture for the Brazilian ICPC Summer School of 2022. In this lecture I'm going to talk about mathematics for ICPC, just a few different topics that I think are important for you to know. So some of them you will surely know, others maybe not. I hope you learned something new today, and these are just the things that I feel are more common and more useful to know. There's obviously a lot of mathematics that you can use in ICPC. This is maybe the basics plus some extra topics I like and I think are fun. Before we start, a disclaimer: I'm going to be showing some code, and this is going to be in C/C++ language. Now, it's nothing fancy, so if you program in Java or some other language, you should be able to translate almost directly to your language of choice. That being said, of course, feel free to ask me questions about the code if something is unclear. Okay, so the contents of today's lecture are as follows. First, I will talk about natural numbers. This includes, of course, prime numbers, factorization, Eulers' totient function, number of divisors, and so on. Next up, modular arithmetic. What it means to work modulo some number m, what operations we can efficiently compute modulo m. So I'll talk about the greatest common divisor algorithm, its extension, the Chinese remainder theorem, and so on. Then I'll talk about matrices, how they appear whenever we want to deal with graphs or with Markov chains, how they can represent systems of equations and how we can solve these systems. And I'll talk about some particular cases and some algorithms that are useful to know to deal with matrices. Finally, I'll discuss the fast Fourier transform and some extra stuff and problems that I find interesting and that you can try for yourself. So feel free to skip things that you know, maybe increase the speed whenever you think I'm going too slow. I'll try to be very precise about things and show you snippets of code so that everything I say is clear. But again, feel free to ask questions during the Q&A sessions or in Gather or by email, however you like, but don't keep your questions to yourself. Feel free to ask them to me and I'll try to answer them. So let's start talking about natural numbers. We all know natural numbers, right? 1, 2, 3, 4, and so on. And an important subset of the natural numbers are prime numbers. So we say P is a prime if and only if P has exactly two divisors, which are, of course, 1 and P itself. So in case you're unfamiliar with the notation, I'm using this vertical line to say D divides P. So in other words, P is prime if the only numbers that evenly divide it are 1 and itself. The fundamental theorem of arithmetic then states that the number n can be represented in a unique way as a product of primes to some powers. So this representation is unique up to reordering of these factors. So you can have, let's say, k primes, and each one with its power e1, e2, and ek. So why is this useful? Well, for any problem that deals with number theory, so with properties of numbers, knowing how to factorize the numbers and find prime numbers and the exponents is important. This includes finding divisors of numbers and using them to do various other calculations. Finally, factorizing a natural number is important when you're dealing with multiplicative functions. Multiplicative functions are those functions that, when you compute them on the product of two numbers that are coprime, then you can compute them on each of these two numbers and multiply the result. So, as I mentioned, for multiplicative functions, the greatest common divisor of a and b here has to be 1 for this to hold. But for completely multiplicative functions, this condition is dropped. So, as you can see, if you can factorize a number, that means find the p1, e1, and so on here, then you can find the divisors, and then you can compute multiplicative functions very easily. So let's start by how do we find prime numbers, which are the key ingredient in the factorization. Well, the obvious method would be, let's ask, given a number n, whether 2 divides n, whether 3 divides n, and so on. If you try all the numbers up to n, and the only ones you find are that 1 and n divide that number, then n is a prime. So this gives us a very simple algorithm to find all the prime numbers up to some given number n. In this code, p, small p, is a stack containing all the prime numbers that we find. Uppercase P is the number of primes that we have found so far. And you should notice that for each I from 3 to n, we run through the primes pj up to the square root of I. What this means is that the running time is controlled by the number of prime numbers up to square root of I. So this is just notation for the number of prime numbers up to a given number. And then this is a running time that is worse than linear, right? It should be worse than ON. But we can do much better. Let's say you have some n, I don't know, n51. Then we can take all the numbers up to 51 and start crossing out those that we know are not prime numbers. So we start crossing out all multiples of 2 because we know they are not and they cannot be prime numbers. Then we see 3 has not been crossed out, so it's a prime number. And we can also cross out all its multiples. We can continue in this way. Whenever we find an uncrossed number, it's a prime, and we can cross out all its multiples because they cannot be primes. Continuing in this way, when we finish, we will only have uncrossed numbers which are prime numbers. So here you can see that after crossing out all multiples of 7, we are left with all 15 prime numbers up to n equals 51. And of course, 7 is sort of like the square root of 51. So we only went up to the square root of n, checking out and crossing the multiples. This algorithm is very simple. It's called the Sifo Veratostenes, and we just have a buffer telling us whether a number is prime, and whenever we want to cross some number, we just set the value in this buffer to false. But we can actually do much better. First, we can start by marking all multiples of 2, and then we can move 2 by 2. Then, instead of storing at each position j here, whether the number is prime or not, that is true or false, we store the number I that we found as a divisor of j. This information is helpful if we want to factorize some number n. What we do is we look into our buffer to see if that number has been marked as having a divisor. Then, if so, we add it to a list of factors here, and when the function finishes, we have the number of prime factors and their list. So the Sifo Veratostenes is O of n log n, and then finding the factorization is just O of the number of divisors of our input. This will be useful, for example, to compute the divisors of a given number. Let's say we have here in f the output of our function fact from the previous slide. In this code, it's important to remember that this should be sorted before used, right? And then we can recursively compute the divisors by just going through the prime factors and calling our recursive function either with 0 times that prime, 1 times that prime, so the counter gets increased here, and so on, right? Up to the number of times it appears on our list. So I encourage you to take a minute to look at this code and maybe try it for yourself. You have to call div of 1, the list of factors, and the range that this list has, and it will generate for you all the divisors of your number n. So what can we do when we can factorize a number and we can compute its divisors? As a first example, let's say you have to compute Eulers totient function phi of n. So this is the number of m naturals such that m is less than n, and we have GCD n m is 1. So that means m is coprime with n. They don't share any divisor other than 1. So the formula for Euler's function is p1, let's say the first prime in our factorization, to the exponent e1 that it appears in the factorization, minus p1 to the exponent e1 minus 1, and you repeat this for each of the primes that appears in the factorization. Remember, we said we had up to pk to the exponent ek minus pk to the exponent ek minus 1. So of course, if we can compute the prime factors and the exponents, we can easily compute Euler's totient function. Similarly, we can count divisors. So sigma 0 of n is the function that counts the divisors. It's the number of d that divides n with d in the natural numbers. So again, we have a formula for this function. Sigma 0 of n is equal to the exponent e1 plus 1 times the exponent e2 plus 1, and so on until the last exponent ek plus 1. So again, once we have computed the factorization, it's very easy to compute any of these functions and use them. Just as a side comment, note that a large number of divisors is obtained, for example, when you have many different prime factors. So you take, let's say 2 times 3 times 5 times 7 and so on. These numbers that have all different prime numbers, these n, have a large number of divisors. And for example, if you go up to 29, this is something like 6 billion, and there's 10 prime factors here, so the number of divisors of n is 2 to the 10, which is 1024, and this is going to be one of the slowest generation of divisors that you will have to do for numbers fitting 32-bit integers. So you see, this is an interesting case to generate test cases for your code. And you should also remember there's similar formulas for other number theory functions, defined, for example, as the sum of powers of divisors. So take all divisors of a given number and sum them to some given power m. There's formulas for this, and all of them you can compute if you know the factorization. So going back to the Eratosthenes sieve, we can still optimize it. For example, we can use a wheel to take dynamic jumps. Let's say not jump every 2 numbers, but jump according to the first few prime numbers. We could also, for example, it's not shown here, but we could also use just 1 bit to mark whether a number is prime or not. But in principle, there's always some trade-off, right, between memory and time. Okay, so the sieve trades off for memory, and it's very fast, but it uses a lot of memory. So here is the sieve. Our naive algorithm was much slower. Okay, this was the naive algorithm, was much slower, but only used the memory required to store the primes. And you can ask yourself, is there anything around here? This is a fun question that was asked by Dijkstra, who you may know for other reasons, but let's see the answer to this question. So, like the naive algorithm, we want to keep a list of primes, right? Keep only the primes that we have found, but do not keep some memory for all the numbers. However, like on the sieve, we will also keep the first uncrossed multiple of each prime. So how do we proceed? We go through all the numbers from 2 onwards, and each time we are considering one, we just look into our list of primes and see whether this number is a multiple of one of the primes we have found before. Then, let's say the number that is uncrossed, but we know is a multiple of a prime, is n, the minimal of them. If I is less than n, then I is prime. If I is greater than n, then we just take n and update it to the next multiple of our prime p. And finally, if I is equal to n, then I is not a prime. The implementation can be done efficiently using a heap. In this heap, we will keep the first uncrossed multiple of each prime we found. We will also have, like in the naive algorithm, the stack of primes. And we will process the numbers from 3 onwards, just taking the first uncrossed number and comparing with the one we are considering. So this algorithm retains the good running time of our sieve, n log n, and it also has O square root of n memory. So it has the best of both worlds, let's say. Okay, so now let's move on to modular arithmetic. We say that a number a is congruent modulo m to r, and I will sometimes say equal r mod m, if and only if we have a is q times m plus r with r 0, 1, and so on until m minus 1. Now, summation or subtraction work just like normal. So if a plus or minus b is equal to c, then it will be the same mod m. The same is true for a product. If we have a times b is equal to c, then a times b will be congruent mod m to c. However, division doesn't work. So if we say A over B, then this can be interpreted as A times B inverse, and then we need to find the B inverse such that B times B inverse is 1 mod M. So in order to compute the division, we need to find this inverse. Now, sometimes you can avoid making divisions. For example, let's say you want to compute the last non-zero digit of some multinomial number, which is in my notation like this, and this is just n factorial over the little n's, n1, n2, and so on, up to nk factorial. Here, the condition for this to be a multinomial number and an integer, the result is that we have the sum over the n's is equal to large N, and let's call this one chi. Then the question is, how do you compute the last non-zero digit of chi? So here it looks like we have to perform a division, right? But what if we factorize all the numbers up here, then factorize each of the numbers down here, and then we work with the factorizations such that we end up just with primes upstairs. Once we have this factorization, this part of obtaining the last non-zero digit just means remove pairs of factors 2 and 5, right? So a pair of factors 2, 5, which is 10, is just a 0 digit in the end. I will leave the actual implementation of this algorithm as an exercise, but let me give you one of the ingredients that you will need, which is modular exponentiation. As part of solving this problem, and as part of solving many problems, you will usually have to compute some number a to the power b mod some number m. Now, how do we compute this? You could say you just take a times as many times a as a to the b, right? So this is just b times. And of course, you can do this mod m. But this would be O of b, and in principle, b can be very large. So how can we do better? Well, we can write b in binary form as z0 2 to the 0 plus c1 2 to the 1 plus and so on, and the last term will be c, and this will be of log b 2 to the log b. Okay? Now, with this expression, if you plug in a to the b, you have that you end up with a product over I and the c's that are different from 0 of a to the 2 to the I. And the key point here is that these are only log b numbers, so our algorithm is O of log b. In code, what we have to do is we go through the last digit of b. If it is non-zero, we update our result by multiplying by a. Then we divide b by 2, which then shifts all its bits one position to the right, and we update a to a square, so that the next time we will use a square instead of a, and this way we construct a to the 2i. As I mentioned before, this algorithm is then O of log b, and it's a very important algorithm. It's very general. For example, here you only have to know how to do a product of two elements, here in this case a. So while I was talking about numbers, you could be thinking about matrices, and this algorithm would also work to exponentiate matrices in O of log b. Okay, so what do you do when you cannot avoid computing inverses modulo m? Well, you use Euclid's algorithm. This algorithm is based on the fact that if A is equal to some Q times B plus R, that is, A can be expressed as some multiple of B plus a remainder, then the greatest common divisor of A and B is the same as the greatest common divisor of B and R. This leads us to the following algorithm to compute the greatest common divisor of A and B. Now remember, A mod B is exactly R here. Now one can show that if you define the Fibonacci numbers Fn equal to Fn minus 1 plus Fn minus 2, then the computation of the greatest common divisor of Fn plus 1 and Fn takes n steps, and because Fibonacci numbers grow exponentially, that means the algorithm is O log n in the worst case scenario. So why is Euclid's algorithm useful to compute inverses? Well, we can prove that the greatest common divisor of A and M being 1 is equivalent to the statement that 1 can be expressed as A times some number x plus M times some number y. Then, taking mod M, we have that 1 is equal to A times x mod M. And this means that x here is nothing else than A inverse. So we just have to keep track of x and y during the computation of the greatest common divisor. We can do this by defining an extension of Euclid's algorithm, where as we recursively compute the greatest common divisor, we keep track of x. Then to compute the inverse, here what we do is we take x and we make sure that it ends up on the range that we want. Now, of course, this will work if the GCD of the number you're trying to invert and the modulo is 1. So we can only compute inverses for numbers that are co-prime with the modulo. Of course, in many problems, we usually take M prime, and then because M is co-prime with all numbers lower than itself, we can invert any number that we want. So now that we have a way to divide numbers mod M, let's talk about one application, the Chinese remainder theorem. This theorem will allow us to solve equations of the form x is congruent to AI mod Ni for some number of equations. Let's say we have k of them. Now, if we have the greatest common divisor of Ni and Nj equal to 1 for all I different than j, then there is a unique x satisfying these equations. Mod n, which is the product of all moduli, The Chinese remainder theorem tells us that in order to solve these equations, we have to define some magic numbers mi, which are the product of the moduli over the j's different than I. Then we compute the inverse of these magic numbers, mod ni, which we can do because, of course, the greatest common divisor of mi and ni is 1. And having these numbers, our equation is solved by x equal to the sum of m bar I times mi times the ai's over all the i's. You can see why. Here we have m bar times m, which they are just inverses, so it's 1 mod ni, and it's 0 mod nj, because the mi's have all the nj's different than I. And then the ith equation is trivially satisfied. In code, what we do is we first compute the modulo n, the product of all moduli. Then we compute the magic numbers, here the mi, and finally we add the corresponding term to the result. Okay, so that's all I'm going to say about modular arithmetic, which comes up very often to avoid large numbers in problems. So now I'm going to talk about matrices, how they appear, what we can do with them, and what kind of algorithms and applications they have. Now, remember, matrices are just collections of numbers. So I can say matrix A is just A1, 1, A1, 2, and so on, and then A2, 1, A2, 2, and so on. And I can have many rows like this up to AN1, ANM. So this would be a matrix A of size or dimensions n times m. So here n is the number of rows and m is the number of columns. Now I will generally refer to matrices as Aij, where I is an index in the rows up from 0 to n minus 1, and j is an index in the columns from 0 to m minus 1. And summation and subtraction of matrices works trivially. So Aij plus Bij is equal to some other matrix Cij, which has the same dimensions as A and B, and its components are just the summation of the components of A and B. The most interesting operation in matrices is the product. So let's say we have a matrix A and we want to take a product with a matrix B. First, we should check that the dimensions are compatible. So A should have n rows and m columns, and then B should have the same number of rows as A has columns, so it's m times, let's say it has p columns. You see the number of columns of A matches the number of rows of B, and then we define the product to be C, where the components of C, Ij, are a sum over K, where A is taken component Ik, B is taken component Kj. Now, if we look at the matrices A as a big set of numbers, B as a big set of numbers, and C as another set of numbers, in order to compute, let's say, the first element here, we take the first row in A, the first column in B, and we sum the products of those elements to get this number. Now, this definition underpins all of linear algebra, and it's very useful for many reasons, as we will see in what follows. But before moving on, I want to mention, for those of you who program in C or C++, a nice way to deal with matrices is to use a list of pointers to refer to them, instead of just passing as arguments the matrices themselves. The reason is, in this way, we can not specify the first dimension of our matrix, and we can just put the number of rows, the number of columns, and the list of pointers to the rows. This makes for very general code that can work for any number of columns and any number of rows. We just have to do some pre-processing, let's say, to save the list of pointers to the rows of our matrices. In any case, in what follows, I will usually work with square matrices, so we will always have the same dimension for the number of rows and columns. So, the first application of matrices that I'm going to talk about is for graphs. Now, for example, you can use a matrix Aij to specify the adjacency matrix of a graph, right? So this would mean, for example, that we can let the element at row I, column j, to be the weight of the edge between I and j, if there is such an edge. Otherwise, we can put a flag, maybe -1, 0, depending on your problem. Alternatively, we may want to specify as the component ij of our matrix the number of edges from I to j. Now, in this last case, we can then see that if you compute the components of I square, right, which is just the sum over k of aik, j, then this is the number of edges from I to k, this is the number of edges from k to j, so the whole result is the number of paths with two edges, so length 2, from I to j. Now, when you compute the product of matrices, the number of operations that you have to do here is n operations in the summation, but you have to do this for each ij, so you have O n cube operations. Now, we can generalize what we saw in the previous slide and say that the nth power component ij of our adjacency matrix is going to be the number of paths from I to j with length equal to n. And the nice thing is that while each product of matrices takes n cube time, because, as we saw before, you can do the exponentiation fast, then this has a log n there. So, in conclusion, one application of matrices and matrix products is computing number of paths in graphs, which actually is also helpful in many dynamic programming problems. And I should mention that, okay, this is the naive way to compute matrix products. There's better ways. You can compute them in O(n) to the power 2, maybe 3, 7, something. But these algorithms are usually too complicated to implement in a competition. So anyway, n cubed is usually what you're going to consider to take a product of matrices. And this can be very useful if n is, I don't know, 100. If n is larger, you will not be able even to compute a product of two matrices. The next application I want to talk about is linear recurrences. So how can we use matrices to represent and solve linear recurrence relations? So a linear recurrence of order k defines a sequence an such that an is the sum of previous terms, let's say an minus small k, for k from 1 to large K, times some coefficients. So the order of the recurrence is this large K. In matrix notation, we can say an is a vector. A vector is just a matrix with one column, and this vector is defined as the product of some matrix, the recurrence matrix, times the vector at the previous index. So expanding, this would be an minus 1, and so on until an minus k plus 1, and this is equal to the matrix R, which I'm going to specify just in a moment, and the previous vector, which is an minus 1, an minus 2, and so on until an minus k. So what do we have to fill in this matrix here, which I called R, so that it computes this recurrence? Well, because an is the product of all these numbers times the c, what we need to do is put here c1, c2, and so on until ck. For the next rows, we can just copy an minus 1 from the first position in the column to the second, which is basically putting 1, 0, 0, 0, 0 up to the end, and so on from then onwards, right? In the end, we will have 1, 0, and many zeros. So now we can also say an is R times an minus 2, and generalizing this, we have R to the n minus the order times ak, where this original ak is just the initial condition for our recurrence. This should be data. So you see once more that if you know R, because you have the coefficients, you know the initial condition, then you basically know any term in the recurrence, and you can compute it fast because you can do exponentiation with the mod-exp algorithm we discussed before. The third application I want to talk about is that of Markov chains, and this is related also to linear equations. So Markov chains are a very general idea. You can think that you have a set of states, let's call them Si, right? And you have some probabilities Pij. This is, let's say, the probability of going from I to j. So being a probability, it's in the range 0, 1. Now, we say a state Sk is terminal if nothing ever gets away from Sk. That means if the sum of probabilities from k to any other state is 0. So you can ask many questions about this probabilistic process. One typical question is, how long does it take to reach a terminal state? So let's say EI is the expected time or number of transitions between states that are required to reach a terminal state. Then, of course, Ek is 0 for a terminal state. That is to say, there's no transitions are required to reach a terminal state from a terminal state. And for all other states, Ei is 1 plus the sum of all the states I can reach from I of the probability of transitioning I to j times the expected time to reach the terminal state from state j. So let's say we know the probabilities, then basically we have to solve these equations to find the expected times when we only know some of them. So generally speaking, the equation we just wrote is of a linear form. That means we have some coefficients, I'll call them Aij. We have some variables, xi, and we can write the equations as the product of the coefficients times the variables summed over all the variables equaled to some independent term, and this repeated for n equations, right? So if we have n variables, we need n equations to solve them, and these are the n equations with the n independent terms. In matrix form, this is written as A times a vector is equal to B, where, of course, the vector B is here. These are the components of A, and x here, we can put it in a vector. So, expanding, we have this equation. In matrix form, we put B1 up to Bn, x1 up to xn, and a11 up to a1n, an1 up to ann. Now, solving this equation is all about moving a to the other side so that we can write x equal a to the minus 1 b, right? But for that, we need to define what the inverse of a matrix is. Because of course, we did define the product of matrices, or matrix times vector, but we did not define the division. To define the division of matrices, or the inverse, what we need to do is, let's say we have an A that has dimensions n times n. We want to find some A inverse such that this is the identity matrix, where the identity matrix is just a matrix that has 1, 0, and so on, and 1 in the second position, and so on. So it only has ones in the diagonal here, and all zeros in all other places. Now, this will be defined only for square matrices and only when something we call the determinant of A is different from 0. So just like you cannot divide by 0, you cannot divide or multiply by the inverse of a matrix that has 0 determinant. So I'm not going to explain how to compute determinants today, but assuming the determinant is not 0, then how can we solve a system of equations? How can we invert a matrix? We just saw that it's about the same thing. So let's remember we had this kind of thing. We had x1 up to xn, and here b1 up to bn, with the coefficients a11, a1n, and so on. Now, the way we solve equations in school is we just isolate one variable. We do this by multiplying and summing equations and performing operations on these equations. But once we isolate, let's say, x1, we remove it from all other equations. So what that means is that we want to take this matrix to the form where there's a 1 here, then there should be something elsewhere, and removing x1 from other equations is putting zeros in this first column. Then, repeating this process for the next variable will lead to having 1 zeros in the first column, then another 1 which isolates the second variable, zeros on the other column, and some other stuff. And we have to repeat this process until we finish with all the equations. Basically what we are doing is we are taking the matrix of coefficients and we are transforming it so that it looks more and more like the identity matrix. When we do this, we operate on the right hand side just like we operate on the left hand side, and this is the standard way to solve equations that we are taught in school. The whole process as an algorithm is called the Gauss-Jordan elimination algorithm, and it's the way we invert matrices, we solve systems of equations. In code, the algorithm looks like this. We have some matrix A. Here, the coefficients I'm putting in another matrix B in case we want to solve multiple times the same equation. If we try to invert the matrix, B starts being the identity matrix, and then we do this process of elimination of one variable. But the only thing that we have to be careful about is that for numerical stability, we want to choose the next variable to isolate and remove from the system of equations to be the one with the largest coefficient. So this is some stabilization of the equations. We also need to check that the matrix is invertible. So this is a check that the determinant is non-zero. And if this check passes, then here, by the end, B contains the solution. So this is very general code to solve a system of equations. It is O n cube as it's been presented here. And well, just like matrix multiplication, we can actually do a bit better, but in practice this is usually enough. In programming competitions, it's very easy to code, and you can solve systems of equations, for example, to solve Markov chain processes. Now, that being said, one thing to keep in mind is that sometimes the systems of equations that we get in some problem are not completely general. For example, you may have a matrix of coefficients A that has non-zero elements on the diagonal. So this is A11, A22, and so on until ANN. but you can also maybe have just two diagonals that are non-zero, and then all zeros here and here. So if this is the case, then using Gauss-Jordan elimination is a bit too slow, or it's suboptimal, because you don't really have to eliminate the full column, let's say, for the first case. The first column, you don't have to eliminate the first column here, you just have to eliminate this term. So you should keep in mind when you solve problems that sometimes you will see, I don't know, n equals to 10 to the 3, and you would say, I cannot use Gauss-Jordan elimination, which is O n cubed. But if you use it smartly, let's say you don't use the full general form, but you just take advantage of the form of your matrix of coefficients, then you may see that you get, for example, O(n) squared. So keep this in mind whenever you see a problem. It looks like a system of linear equations. If you have too many equations, maybe you have to figure out some special structure in your matrix such that you can simplify the algorithm until it's fast enough. So just a final couple of comments on matrices. One of them is there are important decompositions that serve for many different purposes in linear algebra, and many of the algorithms that you can think about that work with matrices will use these decompositions, such as the LU and so on. So it's sometimes useful to know and have some pre-written code to get them. Another comment is that if you can show that you can multiply matrices in O t of n some time as a function of the matrix size, then computing inverse of a matrix is also O t of n. So these two are very much related, and the relation is deep, and it's something that you should keep in mind whenever you see a problem about computing inverses. Maybe you should also think about multiplying matrices and how to obtain the solution in that way. A final comment is that there's many generalizations of linear recurrences and how you treat them with matrices. So you can deal with coupled systems of linear recurrences, you can deal with inhomogeneous linear recurrences, and so on. So maybe look into how to generalize what we showed for a simple order k linear recurrence to some more general cases which may appear in some problems. Okay, so now I want to talk about fast Fourier transforms and how they can be used in a competition. So a Fourier transform of some function I will call f of omega, and this is defined by the Fourier transform operator acting on some function f of x, and this operator computes the integral from minus infinity to plus infinity over the variable x of the function that I originally have times some exponential factor, which in my conventions will be 2 pi I x omega. Here omega is what we say a frequency, and x here is a coordinate. The inverse transform takes f of omega and gives you f of x, and it's just an integral from minus infinity to plus infinity in frequency space of the transform function times the inverse coefficient with 2 pi I omega x. So Fourier transforms have lots of nice properties. One interesting one is called Poisson resummation, and this says that if you take the transform and sum it over all integers, actually the result is the same as not transforming. So this is a very nice property called, as I said, Poisson resummation. But today I'm going to concentrate on convolutions, which I'll note with a star, and I define like this. If I have two functions, f of x and g of x, the convolution f star g is the integral from minus infinity to plus infinity over some auxiliary variable y of f evaluated in y times g evaluated in x minus y. Okay, this is a definition of this operator, which I call convolution. Then, a nice thing about Fourier transforms is that if you take the Fourier transform of the convolution f star g as a function of x, so you transform that, and what you get is the transform of f as a function of omega times the transform of g as a function of omega. So, essentially, Fourier transforming converts the convolution into a simple product. The key point here is that the convolution is non-local. That means to compute a single point in x, you have to consider all y's. But here, when you compute the transform of the convolution, this is a local operation. So to compute for a single omega, you need to compute only f tilde at that omega and g tilde at that same omega. Of course, in practice, we don't work with continuous functions. We usually work with sequences of numbers, and then you define the sequence transformed as just a discrete Fourier transform, which takes all your elements in the original sequence, fn, and multiplies them by a discretization of the exponential factor I had before, okay, n over large n. So if we have n numbers in our sequence, here we get n transformed coefficients in our transform sequence. Then the convolution can also be discretized, and when you do f star g, you have a sequence that is defined as taking m from 0 to n minus 1 of fm times g, where here you need to take n minus m and make it periodic by taking mod large n. The convolution theorem that I explained before for the continuous case now simply states that this discretized transform of the convolution is nothing else than the product term by term of the transformed sequences. Now, one should observe that if you compute the convolution in this way, you have n terms, right? And you have a summation over m terms again, so you have O n square time. Whereas here, if you have fk and gk, you have On to compute the transformed of the convolution. So the idea is you start with two sequences fn, gn, you then apply the operator for Fourier discrete transform, then you obtain f tilde k gk, you then take their product, fk tilde times gk tilde. Then you are ready to apply the inverse operator. And finally, you recover f star g n as a sequence. Now, we said this is On. We just need to analyze how we can do these two operations fast, or at least faster. We want to be faster than On square. The key point to do this is to note that when you compute the transform, let me copy the definition here, was from n0 to n minus 1, fn, and the exponential factor over n kn. Then splitting the even and odd terms, we have that this is equal to the sum up to n over 2 minus 1 of f2m with an exponential term that is very similar but has n over 2 here, km, plus we take outside some factor e to 2 pi I n k, sum for the odd terms, which is f2m plus 1 e to the minus 2 pi I over n over 2 m k. So we get that this is some ak tilde plus an exponential factor 2 pi I over n k times some bk tilde, where this guy is the first term here and this guy is the second term here. And we see that here ak tilde has period n over 2, bk tilde has also period n over 2. The original one, fk, had period n, and the twiddle factor, this is called twiddle, this factor has an anti-period, so it changes sign when k goes to k plus n over 2. So to compute fk, we have to do ak plus the twiddle factor 2 pi I over n times k and times bk, and this is going to be alright for k 0 up to n over 2. Of course, I'm assuming everywhere that n is even. Then if k is larger than n over 2, what we have to do is just invert the sign before the twiddle factor. Again, this holds for k 0 to n over 2, but now we are computing the second half of the transform. So essentially, we have reduced the problem of computing fk to computing two halves of fk and then recombining them, and this can be done in linear time. So this should remind you of merge sort, and of course the execution time for this algorithm is like sorting O n log n. The only thing to keep in mind is that here it's very important to divide n by 2, and in order to do this as many times as needed to reach the end, we need n to be a power of 2, so 2 to some number. This is not usually a problem because, let's say you have a shorter sequence, you can pad it with zeros up to the next power of 2. What I have described is called the Cooley-Tukey algorithm, and it's an algorithm that is very simple. It allows you to compute fast Fourier transforms in O n log n. So to compute the discrete transform of some f, you would do FFT of the array where you have your sequence, the array where you want to put the result. We put a 1 for the first recursive call, the number of elements, and 1 to state that you want the transform. And if you want the inverse, then you have to put a minus sign there, and of course just put your transform and your coordinate space sequence in the reverse order. So this is all I want to say about the fast Fourier transform. I want to just point out that it's a very short code, so it's actually a simple thing, even if maybe mathematically it's more complex than other things that we have seen. In code, it's very simple, it's very elegant, it's very fast, and it can be useful in ICPC problems, in particular in many dynamic programming problems, where in the end the whole thing is computing a convolution. Well, if you can manage to state the problem in terms of computing a convolution, then the fast Fourier transform will do the job in O n log n, when you would have a very hard time to think yourself of an n log n algorithm. Okay, so we have reached the end of this lecture. I want to just quickly comment on some things that I did not cover. So we did not talk about polynomials, how to evaluate them, how to use them, what's their properties, the operations. These can appear in some ICPC problems. We also did not talk about evaluating mathematical expressions. This is essentially parsing, right? If you get some expression like, I don't know, like 5 plus 7 as a string, how do you transform this either into a tree or some other structure, saying, for example, you could say this is a plus and it joins a 5 and a 7, or you may actually want to directly evaluate this and get the result. Now, this is a very broad topic, and there's lots of things to say about languages and grammars, but it's very interesting and it's very powerful once you know the basic way to write a parser. Then we also did not talk about numerical integration and all the techniques that are associated to it. So numerical integration will help you whenever you have some continuous variables and you want to do some computation with them. Usually these computations involve integrals, and there's various methods, including Monte Carlo methods. So these are just some of the things that I did not touch, I did not discuss. I encourage you to go and look for yourself. If you don't know them or you don't know what I'm talking about, you can ask. And otherwise, anyway, please remember to ask questions about what we covered today or other topics in math for ICPC that you're interested in or that you think could be useful. And I hope you have learned something. See you next time.